everybody. So there is something very nice, something very nice. In fact, in sklearn, we call it pipelining or pipelining. It's called pipelining in sklearn, in fact, which is very important tool. We need to start using it from day one. In fact, when you are building your machine learning models, you can just put all things in this pipeline. It will make life much easier. It consists of some steps. Those steps which we just do every day. I mean, data pre-processing first, maybe some dimensionality reduction, number 2, some steps. Maybe number 3 will be training a model, right? And so on. So in fact, this pipelining, it's a way to combining things into one compact code or one compact workflow. So, machine learning pipeline. The pipeline, in fact, it's created to allow data flow from its raw format to some useful information. Raw format, we import data from files, we get data from sensors, it's raw form, and after that we will do some data pre-processing, min-max scaling, standardization, for example. Maybe we will do some feature extraction or feature selection. Maybe we can do some dimensionality reduction using a principal component analysis, and after that we will train a model and test a model. So pipelining, it's a way for creating a workflow which can combine all those steps into one nice and compact code. It provides a mechanism to assemble several steps that can be cross-validated together while setting different parameters. Also, sometimes we have, we have lots of hyperparameters, and we need to check all those hyperparameters in the same way. So it will be nice also, I mean, building this pipeline, it will help us also for testing those different parameters at once. And it will come back with a good set of combinations. In fact, it will return a good set of combinations. Also, it improves the performance and organization of the entire modeling process from data into model production. I mean, we need to be more efficient. So when you are using this pipeline, life will be much easier and it will be more professional, in fact, for building models from data collection until we have production and implementation, in fact. And it supports scalability. In fact, I mean, you can scale your model. I mean, we build a models maybe for prototypes for maybe subset of data. It will help us to scale the model to scale it up and down. So we have some block diagrams here, for example. I mean, we can start from some historical data. We collect data or some historical data. We can do some feature engineering, right? We can do some feature engineering. I guess I lost my pen somewhere. Yes, just 1 second, please. Okay. All right. As you can see here, for example, we can start from building from some historical data, maybe some feature engineering, maybe including standardization, min-max scaling, and so on. You need to propose a model and train this model, for example. And check accuracy here. When you are happy with this one, we will go to the deployment. And in the deployment, we will connect our model for streaming data, for getting data in real time, for example. And of course, it's like principal component analysis. If you will apply principal component analysis here, we need to apply principal component analysis here. If you will apply min-max scaling here, we need to apply it with the same values here, min-max scaling, right? So we need to get the same set of features or process the features or engineer the features. So, and after that, we deploy it and maybe comparing between different models and so on. So having this pipeline, it will make life much easier. So pipelining, in fact, it makes your workflow much easier to read and to understand, because we will combine sometimes when you are working, maybe one block of code for data pre-processing, one block of code for principal component analysis, maybe also autoencoder, whatever. So your code will be scattered. In fact, it will be fragmented. So one way for making things more organized and more readable is to use this pipelining of machine learning workflow. It enforces also the implementation and order of steps in your project, because we have some orders. In fact, sometimes when you are just doing it, some idea, it will come to your mind, you will try to test it, copy code from one part to another part. So at the end, it will be hard to read the code, and maybe if you will leave it for some few weeks, it will be hard to go back to it. It will be hard to understand, really. So when we use this pipelining, it will enforce us, in fact, to have a kind of order of steps, so things will be much easier. It will make also your work much more reproducible. If someone wants to just take this work and try repeat it, get the same results again, it will be just easy to just run it. He will get all figures, get all confusion metrics, all numbers. And it consists of some steps. It's like transform, fit, predict. I mean, transform, it's about transforming data from one form to another form, for example, fitting your model, training your model, and predict at the end, right? Because when we deploy the model in real life, in fact, we predict. We get data, apply it to the model, and we classify or predict, for example. So I will have this example, iris dataset as well. So as you can see, iris dataset, we can get it from scikit-learn datasets. And we have X and Y, all data points for features. And this is just as a plot. This is the plot of your dataset. And I will try also to import some models, for example, perceptron and SGD classifier, for example, from linear models. And I will use also BCA, right, principal component analysis. And I will do some data pre-processing, such as standardization and min-max scalar, right? Min-max scalar, we try to put all data points or features from 0 to 1. We need to map it into numbers between 0 and 1, and it's useful for different activation functions. And the standardization, in fact, we try to get mean value equal 0, standard deviation equal 1. So mean will equal 0, and the standard deviation will equal 1. So those are the data set. I plotted it with two-dimensional space using sepal length, sepal width. As you can see here, we have 3 classes, right? And in fact, I split the data. I try to use here, maybe I try to split the data using for hold-out validation. So I used, I guess if you didn't specify it here, if you didn't specify in train test split, it will be 80% training, 20% testing, correct? Or 70%, I don't remember. 70%? I mean, we need to sum it, right? I don't remember. Is it 80% by default or 70%? Mm-hmm. Yes. So I divided the data into, I split the data into training and testing, and this is and I used the stratify. Do you remember stratify equal y? What does this one mean? Do you remember stratify? Yeah, stratify. This is very important to get all classes equally represented in the training and testing. So we have 37 class 0, 37 class 0 is 38. So this is the best way for doing it, because we cannot have 37.3, for example, right? So, and also for the test, it will be 13, 13, and 12. So I mean stratify, we use the stratify equal y or equal labels. We use this one to have all classes are equally represented in the training and testing. Yes, again, I want to use principal component analysis for this data set. If you want to use principal component, we just used it before. We have, I mean, I will do it for the 4 components, for example. I will select it for the 4 components because I need to see what I mean, I mean, you can select any component. As I told you, this any component, it could be a number and it could be a ratio, right? So if you want to keep variations equal 80% of information of the transformed of the reduced data set, you can just select this one equal 0.8, for example. It's okay. Or you can select a number of components. So and you train it using X because it's unsupervised, right? Principal component analysis, it's unsupervised. So we train it using only X. If you want to plot the, or if you want to get the explained variance for each, in fact, this explained variance for each principal component. So when we print those numbers, we will get those numbers here. For X1 or principal component 1, in fact, this one should not be X1. This one should be principal component 1. This one should be principal component 2, right? Because the order in descending order, right? From high to low. So this is so if you use the first principal component, you will keep 92% of variation in the data, right? I have my data set, and my data set consists of 4 columns, right? So we have here X1, we have X2, we have X3, we have X4. We will use principal component analysis. So when we use principal component analysis, we will get 4 principal components: principal component 1, principal component 2, principal component 3, principal component 4. If you will use principal component 1, you will keep 92% of knowledge, information. If you will use principal component 2 alone, you will have 5.3% of information. If you use principal component 3, you will have 1.71%. So maybe it's logic. I can train a model using maybe only principal component 1, or only principal component 1 and the principal component 2, for example. You will get very good results.
And so we could do this like the classification with just 1 or 2 feature after the PCA?
Yes, this is correct. So after PCA, you need to select how many features I want to use. So the original data set has 4 features, and after applying a principal component, you will have, in fact, exact same number of principal components. So we call it PC1, PC2, PC3, PC4. Each PC1 will give you amount of information from the data, or variation from the data. If you will use only one principal component, PC1, for example, you will keep 92% of knowledge of information, for example. If you will use principal component 1 and 2 together, maybe it will be 97, 98%. So if you will use BC1 plus BC2, BC1 plus BC2, you will get maybe 98%, which is very good. So in this case, I can lower the dimension of my data set, and instead of using 4 inputs, I can use only 2 inputs, 2 principal components. So if you want to print those explained variance, you can just do it using this one. And also you can sum it, for example, right? And this is cumulative explained variance, this one. So this is the cumulative, this one, this curve, in fact, this is, so maybe this one, it's 92%. If you will use a second component, it will be almost 98%, right? If you will use the third component, it will be almost 100%, you see? So you can just say, okay, I will use 3 components because 3 components will give me 100%. But maybe 100% is not very important. So you can just say, no, 98% is very enough. And you can just keep only. So you need to print this curve. When you plot this curve, this one, we call it cumulative explained variance. And you can select from here how much principal components you want to keep. This is one way. Another way, you can just, from this n components, you can select a ratio. This ratio will be the desired explained variance, which we need to preserve. You can just say, okay, I need to keep only 90%. So I will select n component equal 0.9, for example. So, and it will give you the number of principal components, which will, to achieve this ratio, for example. So this is principal component. So principal component is very, very important. Later on, maybe today or next week, for example, we will study also autoencoder, which will do the same, but autoencoder, it's feed-forward neural network. So this principal component analysis, it's a statistical tool, but the other one, I mean, the autoencoder, it's nice because we can build the autoencoder and we can combine it with my model, in fact. So it will be like buffer in your model. It will get all inputs from outside and it will reduce it and it will deliver it to your model. So you can get one set or one model, one complete model. I don't need to keep this transformation matrix and so on, because also transformation matrix, if I need to retrain principal component, I need to keep all data points and retrain the, so it will be more complex. Maybe it's the same also for autoencoder. Yeah. So do you have any question for this graph here? Any question for this graph? Maybe if you are working in a problem also, maybe you need to test principal component analysis. You can test also autoencoder and have this graph, for example, to explain. It will be nice information. So if you are writing a paper or conference paper, maybe this information also will be useful.
Is this PCA part of sklearn or is it another?
Yes. We get it from sklearn.
Okay, thank you.
So do you see principal component analysis? We can get it from sklearn.decomposition. So it's very easy to use, as you can see here, very easy. Just you need to specify number of components, and you need to train it using X, right? And that is it. And after that, of course, there is one more line for transforming from original set of data into reduced set of data, right? So we can just have something called the BCA.transform and inverse transform if you want to reconstruct the data using a subset of features. Yes.
And another question?
Yes.
The PCA would be the one we would use in unsupervised learning if we do not know the labels for our samples, for example.
No, in fact, for this problem, we know the target features, right? We know labels, but we are not interested in labels. Principal component, try to compress features, try to reduce the dimension of the feature. So we don't care now about target features, right?
Okay.
Mm-hmm. So you have an images, for example, and I want to classify this image. Is it cat? Is it dog? But at that stage, in fact, no, I want to reduce this image. I want to reduce the size of the image. Maybe the image is high definition and it has lots of big areas. You know, the problem here, maybe you have an image and we have in the image here cat in the middle, but we have so much big areas, white space, white pixels, right? So maybe those pixels are not very important. Is it correct? It does not carry any information for me. So we try to get rid of those pixels, which it's redundant because it's all are white in all images. Because when people take images of cats and dogs, almost all cats and dogs are located in the middle. We have big space, big white pixel values. We don't need it. So we try to reduce the dimension of the image to make the training process more faster and much easier.
But what would this practically do in the case of a cat? Would it just take away these pixels that are not useful, or would it what's the process?
Yes. If you can just imagine, we have a bunch of images behind each other like this one, and each image has different cats and different dogs, for example. So we try to select a subset of pixels which carry lots of information, the most of the information. Not all pixels have any information, right?
Sure.
Because when people take pictures of objects, they put the object in the middle. So we have big white area around all images. So if you can put those images in a stack, for example, behind each others, you can just imagine that there are some pixels, we don't touch it at all, we don't use it at all, right? So it does not carry any information for my problem. So we try to get the most important pixels which carry some information or have some variations or so this is the idea behind it.
Yeah, okay.
Mm-hmm. Yes. So are you ready for creating a pipeline? Mm-hmm. So now we need to create a pipeline of this machine learning pipeline, and it consists, in fact, of it consists of 4 steps. No, I'm doing it here for 4 steps, but you can do your own pipeline in different way, for example. So to build a pipeline, in fact, or to construct a pipeline, we will use it also from sklearn, sklearn.pipeline. So first we need to get this one. pipeline from sklearn.pipeline. We need to import it. And you need to define the steps, how many steps you want. For example, I need to, for example, first of all, I need to do min-max scaling, right? So maybe this one will be step 1, for example, right? Maybe I need to reorder it. Maybe this one is step 1. I need to do min-max because all features are coming. The range of all features is different, but I want to do this min-max scaling, so all features are between 0 and 1, correct? We do it column by column, right? So maybe I will start by this min-max scaling. It will be step 1. After that, maybe someone else, he want to do standardization, for example. I want all my features to have a mean value of 0 and the standard deviation of 1. So I will use this one. So this one will be step 2. Correct? For your problem, maybe you will decide that I will build a perceptron. I want to use a perceptron. Someone else will use MLB. Someone else will use support vector machine. Someone else will be deep learning. Correct? So imagine here that I want to use a perceptron. No, sorry, before perceptron, I want to use dimensionality reduction. So now all my features are normalized. All my features are standardized. I want to use principal component analysis. So principal component analysis will be step number 3. Right? So it will be like this one. I need to reduce the dimension of my features because when we use min-max and the standard scalar, for example, we didn't reduce it. It's still the same number of features. But sometimes we have some overlap, some correlation between features. So I want to select maybe the most important. Maybe I want to select to reduce the dimension. So I can use BCE. Maybe someone else will use the function select k-best. You remember it? This select k-best. We used it last slide. Do you remember it? From sklearn. I want to select the most important 2 features or 3 features. So it's up to you to select steps, how many steps you want, and what kind of steps you want to use. But here in this example, I will use principal component analysis to reduce the dimension of my data set. And the final step will be the model, right? Step number 4, it will be the model selection. I need to select a model. So based on your experience, based on my problem, I will select a perceptron. Maybe someone else will select SGD classifier. We need to have only one model in the pipeline, correct? Only one model. So I will select, for example, a perceptron. So now, after that, those are my 4 steps, which I will use, for example. After that, I will build a pipeline or different pipelines. So imagine that I will build pipeline 1. So pipe 1 equal pipeline, and I need to specify steps. So the first one steps, it will be min-max, standard scalar, PCA, perceptron, right? Maybe someone else, he will just say, okay, no, I need to have different pipeline. So this is the beauty here. In fact, you can define different pipeline very quickly. So maybe someone else will say, no, I need to build a pipeline for adaptive linear neuron, for example, correct? Or SGD classifier or whatever, MLB. So you can just select and this is the configuration of your pipeline, and it's based on the problem itself. So just imagine, and as I told you, it consists of transform, fit, predict, transform, fit. So transform, this one, it's a transform. We transform data, and after that, fit the model, right? It will be like this. So now I have a pipeline. If you want to display some certain step, you can just pipeline.step. If you want to display step 0, for example, it will tell you that it's min-max scalar. If you want to set a parameter, right? Because I have here, for example, a perceptron. Do you see a perceptron here? I need to specify the learning rate in this perceptron. So you can just use this command, pipe1.set parameter, and I need to set the learning rate of the perceptron equal 0.5. So this is how we do it. If you need to set a parameter, you can set a group of parameters at the same time or parameter by parameter. So if I want to specify because if I didn't select here I'm using perceptron with default values, and the default learning rate will be 1. If you want to change it, you can just specify it here, pipeline.set parameters. So now I changed it. In fact, do you see? I changed it into 0.5. So there are many parameters. So there are many. You can change, for example, maximum number of iterations, validation fraction. It's 10% used for validation. If you want to change it to 20%, early stopping, it's not working now. If you want to make it true, you can activate early stopping. For the principal component, maybe I can specify number of components, because if by default it's a 3, right? 3 principal components. But if you want to change, you can just change. You can select different solver, for example, and so on. So in fact, you can do many things. So the pipeline steps here, the 4 steps here, consist of minimax scaling, standardization, principal component analysis, and the modeling part. So after that, now I created my pipeline. After that, I want to train my pipeline, similar to training a model, right? So it will be just the same. So I specified here, for example, number of components equals 3, and I specified the learning rate equal 0.2, for example. So the learning rate of the perceptron will be 0.2. Number of components in principal component analysis, it will be 3. And after that, I will fit it using X-train and Y-train, right? Just to train your pipeline. So in this case, we will use X-train, Y-train. In fact, for first, we will go through min-max. We will do this min-max scaling, and after that, we will do this standardization. And after that, we will apply those data to the principal component analysis for extracting 3 parameters, right? 3 principal components. And after that, we will train a perceptron using the 3 principal components from this step, using learning rate equal 0.2. So and I selected here this verbose equal true, so I can see the steps. So first, we processed this min-max, and it takes maybe this 0 second. It was very quick. In standard the scalar, we did it first second, because this is a second step of 4. It take also very short time, and we did principal component analysis, and finally we trained a perceptron. And we will get training score and the testing score. We will get those 2 numbers, training score and the testing score. I mean, you need to print it. In fact, pipe1.score, X-train, Y-train, you will get training score, and using X-test and Y-test, you will get testing score. So the training score was 83% or 84%, and the testing was 81%. So do you see, is there any difference? Do you feel any? So now we can compact all things in very short, very compact line of code, right? And when we train the model, we can just train the model using different set of parameters at any point. You can select different combinations of parameters and train your model, and it will be very short code, very compact, very easy to deal with. And what about prediction? If you want to predict, simple. It's just a pipe1.predict using X-test. You will get your predictions. And if you want to get confusion matrix, just plot confusion matrix for the true. This one, it's the true labels against the predicted labels, which we got from the prediction step. Precision score and the recall score, we can get it also. We can get it also using this precision score and recall score, which we imported from sklearn.metrics. You have we have the code, so we can go to the code and we can run it. Any questions, please, regarding this pipelining or pipeline?
Can I ask 2 things?
Yes, please.
This PCA thing, we always apply it to this min-max and to the standardized data, right? It should be prepared before. And
the principal component?
Yeah.
No, it's up to us to decide, right?
Oh, okay. So we don't have to pre-process the data in order to...
So you can make it first. So if you want to have a principal component first, and after that do min-max for principal components, you can just do it. If you want to change the order, you can change the order.
Okay, so the PCA doesn't have to be applied to the already standardized scale data, right?
Now we do first. Now we applied min-max scaling first for the raw data. I mean, we will get, look, this is pipeline like this one. First, we will get this raw data here, right? Raw data. First, we will do min-max scaling, and after that, min-max. And after that, for those min max scaling, all features now will be in the range between 0 and 1. We will do this standardization here. So all features here will be from 0 to 1 with mean equal 0, standard deviation equal 1. And after that, we will do BCA. So here we will get 3 principal components. And after that, we will do modeling.
So would the result be the same if we did, let's say, PCA first and then min-max and standardization?
We need to test it, right?
Okay.
But I guess...
And another thing, this min-max is basically normalization, right?
Normalization, yes, that's correct.
Okay, okay. Thank you.
First we normalize, because it looks like normal that first we normalize the data, and after that standardize it, for example. Maybe use BCA to reduce the dimension, because the dimension here will be 4, right? So we have 4 features. If we are using iris dataset, we have 4 features here. So after 4 features, we will apply principal components. So we will get 3 here. So after that, we will build the model. So the model here will have 3 inputs, right? Principal component 1, principal component 2, principal component 3, and the output will be the target, right? So you can do lots of stuff here also. So if you have missing values, how you will deal with missing values. If you have categorical variable, you need to convert it into numerical. So you can add more steps here in those 4. It should not be 4 steps, it could be 6 steps, right? So the number of steps, it's according to how your data look like and how much you want to pre-process your data. We can select, and instead of using BCA here, you can select use select k-best, right? So we can use this function here to select the most important 3 features or 2 features from the 4 features which we have. So the order, it's up to you. Each step also, which function you want to select, it's up to you. And the most important for us is to build this pipeline, because this pipeline will make life much, much easier. Right? Yes. Any other questions? Can you see that? Can you do it now? Because some of you, or most of you, in fact, started working in your project. Can you go back to your project now and try to build a pipeline and have all those steps inside? So the code looks, it will look compact, and it will look maybe efficient and easy to read, easy to understand, because we can just say, okay, now I have 4 steps, 5 steps, 6 steps. If you want to add a new step, you can do it. If you want to change some parameters, some hyperparameter, you can do it. So it will look more, maybe more professional or more easy to deal with. Yes. Any
Can
question?
I ask one more thing?
Yes, please.
Sorry, it's me again.
Mm-hmm.
Last time I think I asked and you advised us to use this Keras framework.
Yes.
How would that? Does it have its own pipeline?
No, no, they don't have, but they use it from sklearn also with Keras.
Okay.
So we have this pipeline in Keras, in sklearn, in fact. But if you want to use it in Keras, you need to use it from sklearn. So you need to.
Okay.
It has a way. I mean, maybe some here who has maybe more skilled, because I didn't do it in fact before. So maybe I need to try, and maybe also some of you can help me also, help us to try to use it in Keras.
I was just wondering if it has its own or it's using.
No, it does not have.
Thanks.
As far as I know, in fact, they don't have it in Keras, but they import it from sklearn. In Keras, they use it from sklearn. So at the end also, you will have nice numbers here. So you will get number how much time it takes in each process, for example. In fact, here we have one model, and we selected principal component, number of components for the principal component analysis. We selected the learning rate, for example. You can select other things, right? You can select a number of hidden layers. You can select a number of units in each hidden layer, and so on. So you can do many things here, in fact. And at the end, we need to check the accuracy, because we selected accuracy score. So we need to get the accuracy for maybe training and testing. So it will be like model.score or model. So it will be the same pipe1.score. And we need to calculate the score for X train, Y train. So it will be training score. And when it's X test, Y test, it will be test score. You can also plot confusion matrix, right? You can have the confusion matrix. because it's the same. I want it for prediction, right? So this step also is very important, because when we deploy it in real life cases, we need to use it for prediction or for classification, for example. So we will use X-test for prediction, and we can print outputs, and we can get precision score and recall score. Yes, it's just something about confusion matrix. I want to talk about confusion matrix one more time. You know, the confusion matrix, we plot true labels or true values against predicted values, correct? So for this problem, this one for test set, this confusion matrix it's for test set. So for example, here we have 13 from class 0 classified as 0. We have 6 from class 1 correctly classified as class 1. We have 12 from class 2 classified as 2, right? So in fact, those values are true, like you can say it's a true positive, right? For each class, because it's not binary classification, it's multi-class classification. This one, for example, it's one from class 1 misclassified as 0. So this one, we don't like this one, right? We have here from class 2 0 classified as 0. This is okay. We have here, this is okay. We have here also problem here. Do you see this one? It's a 6 from 1 classified as 2, right? So it's a 6 images or 6 flowers from class 1 classified as class 2. So this number is very bad also. We don't like it. So in fact, our goal is to try to maximize numbers across this diagonal, right? We try to maximize numbers across this diagonal. The summation of those numbers are correctly classified. So if we need to calculate accuracy, so it should be 13 plus 6 plus 12 divided by total number, which is 38. Because we have 38 cases here in the test set, we have 38 instances or 38 classes or examples. So if you want to calculate accuracy, so it should be 13 plus 6 plus 12 divided by 38. So it will be 81%. This is my accuracy. So when we use a perceptron for solving this problem, we will achieve accuracy equal 81%. But also there is something called the precision and recall. Precision and recall. How can we calculate precision and recall? First, what is recall? Recall, it's the portion of actual positive which was identified correctly. So it's the amount of positive cases which was identified correctly. For example, so recall will be connected to the true labels. In fact, this recall, how many positive cases classified as positive. So for example, from case class 0, how many class 0 was identified as class 0? How can we get this number? So it will be like this one. So we have 13 classified as 0, we have 0 classified as 1, 0 classified as 2. So the precision or recall for this class, it will be 13 divided by the summation of by this total, in fact. So because we have 0, 0, so it will not be very clear. So it will be 100%. We can go for class 1, for example. How many class 1 are identified as class 1 or identified correctly? So so from class 1, this is class 1 in total. We have 13, right? How many of those are correctly classified as 1? So we have 13 class 1, and we have only 6 identified as 1 or classified as 1, correct? So we have 6 divided by 13. So 6 divided by 13, it will be 46% for this class. So the recall for this one, it will be 46. So we have a problem here, in fact, which we need to fix. So if you will calculate the accuracy from the code, you will get this in total. I don't know what is the problem in my model. Maybe my model was, I mean, as we can see it here, this model is very good for class 0, is very good for class 2, but it's very bad for class 1. If you will get this number directly, you will not be able to diagnose this problem without confusion matrix. But if you have the confusion matrix, you will be able to identify those problems. So the recall here for class 1, it will be 6, because this is a portion of class 1 which was correctly classified as 1. So it will be 6 divided by 13. For class number 2, it will be 12 divided by just 12, it will be 100%. So in fact, this model is very good for class 0. Recall is very good for class 0 and for class 2, but the performance is very bad for class number 1. So we need to know why. Maybe we need to get another model. Maybe we need to play with the data. I don't know. Maybe there are many reasons, right? We need to try to figure out why. So this is about recall. So now for class 0, we have 100%. For class 1, it's 46%. For class 2, it's 100%. What is the average recall? So we can just get the average recall, this one plus this one plus this one divided by 3. So it will be 82%. So this is average recall. For precision, in fact, what does it mean precision? It's a portion of positive identified was actually correct. So in this case, we will look into predicted. So this is a portion of positive. This is a portion of positive identifications that was actually correct, right? So we will go for example, for class number 0, right? Because for class number 0, this one will be positive, all the rest will be negative, just to try to convert it into binary classification problem. So when we focus on class 0, we assume other classes as negative. So here, how much from what portion of positive identification was actually correct? So look, we have here 14 identified as 0, correct? We have 14 identified as 0, but in reality, how many actual zeros here? How many actual zeros? We have only 13, correct? So it will be 13 divided by 14, right? So because in my data set we have 14 predicted as 0, 6 predicted as 1, 18 predicted as 2. But in reality, what portion of positive identifications was actually correct? So from those 14, we have 13. From those 6, we have 6. From those 18, we have 12 correctly classified as 2. So it will be 12 divided by 18. It will be 6 divided by 6. It will be 13 divided by 14. So the precision will be, for class 0, it will be 92%. For class 1, it will be 100%. For class 2, it will be 66.67%. And at the end, we will get, I don't know what is this. What is this?
This is not correct. I think this is not correct because it should be 86%.
The precision?
Yeah, the total.
No, I don't know what is this. I have no idea what is this.
I think it's just a typo.
Yeah, it's 86%. This is correct. This is the precision. This is the average precision. It will be 86%. But I don't know what is this.
The 12, I think, just repeated again in this.
No, maybe I want to get this one. I need to get this one. So maybe this is not correct. It should be 13 divided, maybe this one plus this one plus this one divided by 38. So this is something wrong. Yes, but we have the average precision was 86%, which is correct. And this one it's 82.005%, so we can have it. If you want to get it in the code, if you want to get those numbers in the code, you just need to get precision score, for example, for average equal macro. You need to select this one macro. So we have precision score. We have also recall score. We have another command similar to this one called recall score. So do you have any questions about the confusion matrix? So this confusion matrix is important. For example, if you are working in medical and building a device for blood tests or whatever, you need to have this confusion matrix. This is very, very important. And as I told you, if you want to go to understand specifically what was the problem, why recall was this value, why precision is this value, what is the problem exactly here, you can identify this from the confusion matrix. So So for example here, from 18, we identified, in fact, my model was able to classify 18 points as 2, but from those 18 points, we have only 12. Only 12 was true positive, correct? So we have a problem here, in fact, in 2, because my model tended to classify many data points into 2. So I have a problem in my model from the precision. From this number, I can discover that my model has a problem in the precision regarding class number 2, because it tends to classify many examples as 2, but this is not correct, because from those 18, we have only 12 were actually 2. So the precision here will be 12 divided by 18. My model classified 6 as 1, but from those 6, in fact, we have only 6 are true positive, right? So the accuracy was 100%. But of course, the recall here was very bad. So my model tends to very conservative against class 1, in fact. So it's very conservative, right? So you can write something in the conclusion. I mean, from the confusion matrix, you can get the confusion matrix from your model, and you can write something in the concluding remarks. Okay, this model work good for this, bad for this? It will be very good addition in your paper. For example, if you can have this confusion matrix and try to explain the meaning of recall and the precision regarding your data points or your problem. Yes. Do you have any question regarding the confusion matrix? So to get the confusion matrix, you have all code. I mean, you don't. I got the confusion matrix from the code here. So just to you can get the confusion matrix and print your confusion matrix. Precision score and recall score, you can get also from the code. It's 3 lines of code. And you will get all those numbers, and it will take maybe half page in your paper, for example, right? So you have the table, you have those numbers. You can maybe write something and explaining those tables. So maybe you can get maybe 1 page, for example, or some paragraphs in your results section from those 3 lines. Here, in fact, I defined last time. Do you remember? Last time I defined 2 pipelines, one for perceptron and one for. I defined one for perceptron and one for this SGD classifier. So I want to train it as well. So it's the same, no problem. So pipeline number 2, I need to train it. So just if you want to print some steps, if you want to change some parameters, for example, I try to select learning rate equal 0.5, and I will train it using X-train and Y-train. And after that, I will print accuracy score for training and for testing. And after that, I will print the confusion matrix. So for training score was 95%. For the testing score was 100%. This one works better, in fact, with my data set. I mean, this pipe 2 works better because the accuracy here, you see, it's 100%. And this is the confusion matrix for pipe 2. So the accuracy recall, all numbers are 100%. So this model works much better than my model. And as you can see here, it was just very easy to define another pipeline and select a different model and make comparisons between models. So now I have 2 pipelines in parallel, and I can just choose the one which perform much better. So I don't need to write lots of code again, in fact, because at some point it will be very confusing in your code, and it will be hard to know which one belongs to what. So I defined a pipeline, and I defined another pipeline with a different model, and I can run the 2 pipelines, and I can just discover, which one is better. So it's easy to know that GDB, this SGD classifier performing much better than a perceptron for this dataset. Yes, so the precision score was 100%, recall score was 100%. So this model looks like much better. Yes. Any question for this pipeline stuff, pipelining? Maybe the final slide will be about search grid. The grid search. I mean, we have this grid search algorithm. If you have different parameters, hyperparameters, and I need to test different values, how can we do it? So for example, in the perceptron, I want to check I want to train the model for 0.1 as learning rate, 0.2, 0.3, 0.4. So I have a range of values or a set of values. Is it possible to use a pipeline for this? So I can define a pipeline, and I want to test the pipeline for different set of values. And also principal component analysis. I want to check what will be the performance if I used one principal component, two principal components, three principal components, correct? For example, if you will select select k best, for example, I want to check for k equal 1, k equal 2, k equal 3, k equal 4. Maybe I need to use cross validation, and I want to select for k equal 3, k equal 5, k equal 7. So in this case, we need to use a technique called grid search. And this grid search, it's one way, it's exhaustive search over specified parameter values for an estimator. It's very simple. We just need to select. I need to select or create a grid of parameters for all different values, and just select an exhaustive search, which means we will run the model for all those combinations, and at the end it will tell you what was the best combinations of those. I mean, this one is very, very practical for us, because sometimes I need to test the model using different techniques, different hyperparameters. So in this case, it will make life much, much easier. So I have here an example. First, we will use this grid search. Grid search also, we will use it from sklearn model selection. So sklearn.model selection, and we will create a dictionary of values. For example, I want to test for principal component analysis for number of components equal 1, 2, 3, 4. So I just specified all 4 values. I have 4 parameters. So I want to check for 1 principal component, 2 principal components, 3 principal components, 4 principal components. Also for the perceptron, for example, I want to check for 0.2 learning rate, 0.5 learning rate, 0.8 learning rate, and 1 learning rate. For example, this is just an example, but you can make it more complex. So for example, you can change maybe the number of units in hidden layer, how many hidden layers, and so on. So you can play with lots of hyperparameter values. So we will create this parameter grid, and after that I will use this grid search. They call it grid search cross validation. With pipe1, this is the model, which I want to test those values with this model. So this model, this one, it could be a model in fact, or it could be a pipeline, right? This one, it could be a model, and it could be, so I can use the same technique with any model with a perceptron. So I can use this one directly with a perceptron, or I can use it with a pipeline. If you will use it with a perceptron, so you will run this cross validation. This is the K value, and this is the scoring, maybe it's accuracy, and this is my grid, right? So now I need to test in one shot. I want to test it for number of components equal 1, 2, 3, 4, and I want to test it for learning rate equal 0.2, 0.5, 0.8, and 1.0. So in this case, in fact, how many components, how many times we will train the model? So I have here 4 times 4, correct? So in fact, I have 16 combinations, right? I have 16 combinations. So I will train this model for 16 times. So it will be, for example, for any component 1 with training rate equal 0.2, 0.5, 0.8, 1.0. And after that, I will go for 2 with the rest, and so on, because it's exhaustive, in fact. So we will test the model with all those combinations, and at the end, we will tell you what was the best combinations of parameters. And I selected here k equal 5, right? K equal 5. So in fact, we will divide the data into 5 folds, right? So we will do this. For example, how many times you will train a model? It will be 16 times 5, so it will be 18 times, right? So we will do it by using this line of code. And after that, after creating this grid search, it will be, you will train this grid search using X and Y, maybe, for example. I mean, maybe here we don't need to have X train, Y train, because I'm using cross validation. So this one should be X and Y. because we are using cross validation, right? We should not use X train and Y train. Maybe we need to do it with X and Y directly because we use cross validation. So, and after that, I want to print the best parameters, and the best score, for example. So we got here cross validation score, best score was 91%. So the accuracy, best accuracy which we got was 90%. What was the best parameters? The best parameters was any component equal 3 and the learning rate equal 0.2. So maybe this one and this one, we got the same best results for 3 principal components and the learning rate equal 0.2. So now it's much easier. So if you have large set of hyperparameters, you can put all those using, you can test all those combinations using a grid search, and it will give you the best score and the best combinations of parameters. And I printed here after training this model, right? I tested this one. I tried to get predictions for X tests and put all those values. You see, I mean, this is in fact it's true values against predicted values labels, and it just works fine. And we have the code here in GitHub. So if you are working with your data at the moment, I'm sure that you are already working with your data. So try to use this approach from the beginning. It will make life much easier. And we need to use a pipeline, because in pipeline we will combine many steps into one workflow. And at the same time, also we can use grid search for testing different combinations of hyperparameters. Yes. Any questions for grid search or pipelining or machine learning pipeline? So you need to practice, in fact, when you practice, but those examples are very simple examples. We have the examples in GitHub. So in fact, you can apply it to your data, right? To try to customize it, try to modify it according to the models which you are testing. So it would be nice in your paper, for example, if you are testing different types of models, you can create one pipeline, and you can create a pipeline for each model. You will run those pipelines, and you will get best results from each pipeline. You can put it in a table, for example, in your paper. So you can make comparisons between different models. It will be nice. So maybe you can just say, I will test a perceptron, I will test multi-layer perceptron, I will test deep learning, I will test this and that. So when we have this pipeline, it will help you to facilitate your work and run different models using the same pipeline, the same strategy, the same steps. So comparisons will have a meaning, in fact, because I cannot, for example, build a model using min max and another model for standardization, for example, and I can make comparisons. Comparisons will not be valid. So if you need to compare between models, I need to have the same conditions, the same steps, the same data pre-processing steps applied to all those models. So you can create one pipeline for each model, and you can use grid search, for example, for training each pipeline, for example, and to get the best combinations. It will add something to your results. For example, you can have one more table, for example, best combinations of parameters for this model, accuracy, precision, recall, right? So you can have a table summing all your results. And instead of training only one model, maybe one reviewer will say, why didn't you try different types of models? So just do it now, right? Just do it now using this pipeline. Using this pipeline approach, it will make it easy to test different types of models very quickly, in fact, and to get your data into your table, so you can avoid some questions from some reviewers, for example. Because some people will just say, okay, you are using deep learning. Why didn't you try to use, for example, try multi-layer perceptron and support vector machine and all those methods? No, it's fine. Just put those into those pipelines, test them, get results, put it in a table, for example, so we can avoid some questions from some reviewers, for example, right? Yes. So any question for that part? So if you are working now with your data, just to try to try to apply those pipelines to compact things together and make things much easier. So should we take a 5 minutes break, for example? Any questions before the break? Any questions? Okay, so I will upload all those material to the Blackboard, and you have the code. Just to go into the code. So if I can share my screen here. Yes, I can show you something also before we leave. So I don't know if you can see. Maybe it's just because my screen is widescreen, but I can share it in another. Oh, sorry. So in fact, this is the code. This is, I call it machine learning pipeline. It's in GitHub, and I start here by we have importing the data sets, and from this data set we can get iris data set, for example, plotting your data set, and after that I tested only principal component analysis, and this is the explained variance for each variable, and this is the sum of variance. If you want to plot those graphs, it's easy. It's just to plot this graph, and after that using a bar plot to plot the explained variance for each variable, principal component. But remember, when we use principal component, the principal components does not have any correlation with the inputs. I mean, there is no meaning. There is no physical meaning for those principal components. So don't expect that someone will say, okay, what was the unit of principal component 1? No, there is no connection because they're just numbers. Creating a pipeline. I created a pipeline here. I used the cross validations and the grid search, in fact. Those are the steps. We need to define the steps: principal component, adaptive linear neuron, perceptron, standard scalar, min max. Define different types of pipelines. So it will make easy, just very, very easy here to define in a number of pipelines for different models. You cannot have two models in the same pipeline. You can have different types of transformation, for example, but not models, because we transform the data for training a model. So you need to have only one model. But for transformation, we can have min max, standard scalar, BCA, select k-based, for example. So this is not a problem. And you can display, you can know what kind of steps, how many steps, and so on. This grid search, it's from model selection. Yes, I defined it here already. Should not define it again. So we have grid search. You need to define the parameter grid. So if you will select BCA 2_n components, eta, you can just define what you want. In the grid search, we can use cross validation and train it. So I selected here verbose equal 10 or something, so I can display the learning process outputs from the training process. So we have 5 folds here for each 16 candidates. We have 16 candidates model, in fact, because for each, we have here 4 times 4 values. So in fact, we train 16 models or 16 candidate models. Each model has different combination. So the first one will, for example, will be n component equal 1. Learning rate will be 0.2. The second will be 1 with learning rate equal 0.5, and so on. So we have 16 candidate models and we will train those for 5 folds. So in total, it will be 80 times for training and testing. So at the end, we will have those numbers, and at the end, we will after that, we will print best set of parameters and the best score, for example. So the best score with 91%, and the best we have best score and the best parameters. So we have command called grid search.best score and the grid search.best parameters. So the best parameters from those sets of parameters was 3, number of components, and learning rate was 0.2. Yes. So I hope that this one will help you to make your code more clear and more compact, easy to work with, because just remember, now you are working in maybe in your first year or second year PhD. After some point, you'll have lots of code, and maybe after 1 year, if you will go back to it, you will just you will not be able to understand or remember what was this for. So it will improve readability of your code when we use pipelining. Yes. So do you have any projects which can be represented today? Is there anyone who?
Yeah, I can present.
Okay, thank you.
Yeah.
So we will take maybe 5 minutes break, and then we can go back to presentations. Should we meet again at 11:25?
Okay.
Okay, so thank you very much.